make it. Maybe it's. Oh, okay. I'm just going to make it. Maybe we come back. We keep this open during class. So this is the location of the International Space Station. Currently, this is the current position, and so it's out over the Atlantic, and the orbit is an hour and a half long. So this is. We'll come back. Jets. It's going to come back in about an hour and a half. It'll be back over South America again. When we started this a few minutes ago, we could see this looked like the Straits of Magellan there. And what we mean here is that in addition to this map, there is a live feed here for the space station. And so you can see the Atlantic right now. We could see the coast of South America there. It was pretty cool. And there are 2 Soyuz spacecraft here docked. So if you can pull this up, if you Google ISS live stream HD, you can find this, and some of the views are really, of course, just spectacular views, and a lot of the time you're just seeing a bunch of clouds. But so you kind of have to just keep checking back, and then of course half of the time it's just dark. You can't see anything. It's pretty cool. I don't know. Maybe we'll leave this on in the background and come back to it in a few minutes and see what they're up to. Okay, so let's see. Wanted to go back over a little bit of the homework. One of the homework problems that I didn't go over. Yes, ma'am.
I just want to say that the bottom half of the screen, which shows where it is, you
Yeah.
can get an app on your phone that has that.
Oh, you could do this on the phone. Okay, but
It
not.
doesn't show the feed though there.
Okay.
But it has what it is.
Okay, so what is today? The 5th. 5 Feb. Okay, so we have a practice test due Monday. We don't have the same setup that we did in the other classroom where I could send people to the board at the same time. So I think what I'm going to do is bring in at least one tablet and put somebody up here at the podium. If you have a tablet, especially a Surface Pro, those have really nice high quality screens on them. The iPads don't work so well for this kind of stuff. If you have one, you could bring it in. We could hook it, especially if you have an adapter. You have to have an adapter that you can plug it into the display here. So I'm going to bring at least one, maybe 2 Surface Pros, and then I'll give you some problems to work on, and then we'll plug them in, and that way we can put it up here for people to see. Okay, so that's what we'll do on Monday. Do the practice tests, and discipline yourself to do it like it's a test, and then the test in class on Wednesday. Okay, so looking at, let's go back. I didn't go over 2 of the problems on the homework from last time, homework from Wednesday, which were the resistors put in series and in parallel. And I wanted to go over that because it gives you some insight into how resistors work. So remember that in the text there are 2 forms of Ohm's Law expressed in 2 different forms. One of them is more fundamental in the sense that it's a descriptive of the material response to an electric field. And the second one we can derive from the first one. So I'm going to start with this first one here and derive the second form. The second form has to do with a circuit element, a resistor, whereas the first one has to do with some material that you might make a resistor out of. So the resistance that's in the second form is actually dependent on how you put the material together. So it depends on geometry, and that's what I'm going to show you here, how this works. So suppose we have some material, and this sigma here is called the conductivity. It is not, here we go, using the same symbol to denote 2 different things, right? Be aware of this. Sometimes we use it for surface charge. Now we're using it to mean something else, which is the conductivity of the material. It's the property of the material. Copper has a high conductivity. Water has a pretty high conductivity. Plastic has a low conductivity. Glass is low conductivity. A superconducting material has almost infinite conductivity is really high. Hard to measure, it's so high. The inverse of the conductivity is called the resistivity. And it's really measuring the same thing just in a different way. It's just the inverse of the conductivity. It's the resistivity of the material. And so if I apply an electric field to a material, I will get a current density in response to that. And remember, the current density is a charge per area per unit time. And I'll get a current density in response. And that current density for most materials is simply proportional to the electric field, the strength of the electric field that's present in that material. And there's actually materials that don't obey this, but or obey something a little more complicated than this. But we're just going to consider the simple case, which is just that if you apply an electric field inside of a material, then you're going to get parts, the charged parts of that substance flowing, moving in response to that. And the measure of that is the current density. The current density, again, is charged per time per unit area. Okay, so let's suppose we took a long cylinder. Make a long cylinder out of that material. And also make a short, fat cylinder. Same amount of material in these two cases. I'm applying the same potential difference across that. So I hook both of these up to a battery, and I want to know how much current is going to flow. And I'm going to find out here in what I'm about to demonstrate to you that you're going to get more current in the short, fat cylinder and less current flowing through the long, skinny cylinder. Now, remember what I mean. What I'm doing here is I'm hooking the same battery up to both ends, so the same potential difference. And we're going to study how this works. Okay. So let's go back to our original equation here, and we're going to make some kind of material out of this, or that is some kind of structure out of this. It's going to have an area. So I'm going to multiply by the area of that cylinder, whether the cylinder is long and skinny or short and fat. It's got an area associated with it. Yeah, end area of the end cap, just the end cap. So in this case, in the Okay, so in this case, I've got a little area here. In this case, I've got a big area. And in this case, I'm going to have a long distance d. In this case, I'm going to have a short distance d. Okay. So I'm going to see how these things depend on the area and the distance, the length of it. Okay, so coming over here to this case, now I'm going to multiply by that area, whatever it is. And J times A is the total current that's flowing in through that device, through that thing. That's the meaning, the difference between the current density and the total current. Okay, and now let's see. Remember, I'm applying a potential difference here, so I've got a battery, and I'm hooking it up to both ends. So there's a potential difference here across this, delta V. And the strength of the electric field that's inside of that material then is going to be the negative of that potential difference divided by the distance, right? This is, remember, the electric field is a negative gradient of the electrostatic potential. And if the electric field is uniform, I can just figure it out, well, what's the potential energy drop divided by the distance? And in this case, if the electric field is in this direction, the delta V is negative, and so I'm going to write negative delta V is a positive number. I'm going to write it as the absolute value of potential drop. Okay, so I can rewrite this as sigma A over D times the absolute value of the potential drop. So you see how the area comes in one way and the length comes in a different way. And that's the important thing here. That will tell us here which is going to get more current flowing through it, a short fat cylinder or a long skinny one. If they have the same amount of material, one of them is current is going to flow more easily through it than the other one. And I'm going to write this in a different way here. I'm going to take d over a sigma I is equal to delta V, and I'm just going to write the delta V as the potential drop. That's the potential I've put across the across this device by the battery here. And this looks like then what we call, this is the second form of Ohm's law here, the resistance. This is called the resistance. The resistance depends on the geometry, depends on the area and the length of the resistor. So there's a material property sigma. In fact, we could say R is equal to D over A times the resistivity of the material. And so you can see here the structure, how I put the material together to make a certain shape. That's what comes into the resistance of the device. So I can take the same material and arrange it in different ways and get different resistance. So how is that? Why does it come out that way? Why does the resistance increase with length and diminish with area? So let's go back to this long, skinny cylinder and the short, fat one here. It's the same amount of material, but this way has more resistance because D is greater and A is smaller. And this way has less resistance. D is less and A is more. So I get the top one has higher resistance than the bottom one, even though it has the same amount of material. So let's think about what's happening here. One way to see it is that I have to push the charge carriers through the same device here, and the carriers have to pass through the entire length of the material. Whereas in this case, the current is going to get spread out over the area. And so it has less material to travel through, so there's less material to resist the flow of the charge carriers. So if you string up the material in series like this, you're going to get greater resistance. If you put it in parallel like this, you'll get less resistance. Same total amount of material, but if you put it up in a different, arrange it in a different way, the resistor will either be stronger, the resistance will either be higher or lower, depending on how you arrange the flow. Okay, now that wasn't quite what I was looking for in the homework assignment. Let's go back and we can get the same thing. Remember, Ohm's law is still captured in this form. You can get the same thing by considering these circuit elements like this. It's the same, really the same argument here. I'm going to take two resistors, R1 and R2, and I'm going to put them in series like that, and I'm going to put a potential across them. This is the potential difference across the pair. And I get a potential drop across this first resistor is V1, and the potential drop across the second resistor is V2. And according to it's similar to Kirchhoff's law, voltage law. It's just a potential drop across the pair is just the sum of the potential drops across the first and then the second. But we also know here that the current flowing through the current flowing through both resistors is the same. It's the same current that flows through both, right? Because it doesn't deviate, it doesn't get split, it doesn't end up charging a capacitor or anything. It just flows through. So the potential across the first one is the resistance of that first resistor times the current, plus the second potential drop is the resistance of the second resistor times the current. It's the same current, so I can factor this out. And what I want to know is the effective resistance. So in other words, the effective resistance of the combined resistors in series. I'm just treating the pair of them as though they were one element here. And so I can see here these two things are equal to each other. So that gets me that the series resistance is just the sum of the pieces of the sum of the resistors put in series. And this is the same thing like taking the material and stretching it out longer. It's the length of the material that you have to pass through. The longer the material, then the more the resistance, depending on D. Okay, but now let's consider the case of the what happens in parallel. Oh, okay. First, special case. Let's suppose that R1 is equal to R2. is equal to R, then in series it's just twice. I can make if I have two 1 ohm resistors, I can just put them in series and I make a 2 ohm resistor by combining them. Okay, now the other way, making the short fat cylinder, it would be like doing this, taking two resistors and giving alternate paths for the current to flow in. It can flow in the top or the bottom. In fact, it will split up. Some current will flow. If I have current flowing in here, some will flow through the top and some will flow through the bottom. So I'll have a different current flowing through these two depending on the resistance. Okay, so now the currents add. The voltages don't add, the currents add. In fact, the same voltage across both resistors, because remember I've hooked this up to a battery here. So the voltage is the same across both resistors. Okay, and so going back to this, remember the voltage, the current is then the voltage divided by the resistance. So the current flowing through the first resistor is the voltage, which is the same on both batteries, divided by the resistance in that battery, resistance in that resistor, and the resistor in the other one. And this is going to be treating this as a lumped element, that is this whole thing looking at the pair. The resistance of that pair is related to the current and the potential across it, like that. Okay, so now you see that the resistances in parallel add inversely, like this. And in fact, if they're unequal, this resistance will be closer to the lower one. Okay, so in the special case here, where they're equal, R1 is equal to R2 is equal to R, we find out that the parallel resistance is equal to 1/2 of the resistance of one of the resistors. And that's because the current can spread out, flow over the area, distribute itself over a larger area. Right, that's what we were looking at before. Okay, so using the circuit laws that we've seen, we can see how to now combine elements. You can do the same thing for a capacitor. You find out capacitors in series add inversely, and capacitors in parallel add together. So you can combine these laws for elements in series and in parallel and so forth. So it gives you an idea for, in this case, for how resistance and resistors work, and you can develop the same understanding for capacitors. If you have a larger area, you're going to get a greater capacitance. So in the case of capacitors, you're spreading it out in a larger area, so the capacitance goes in the opposite direction. The capacitance is proportional to area and divided by the distance between the capacitors. Okay. All right. Any questions about that? We're not spending very much time on circuits. There's a lot of interesting stuff you can do with circuits, and we're just not spending very much time on it. It's kind of too bad. You'll get to spend more time on it, I guess, when you're doing your experimental course. You'll spend more time on understanding circuits. For now, it's the purpose of it in this part of the chapter, in addition to giving you something interesting and concrete and practical to do, is as a concrete practical example of electric fields and potential energy, of potential differences and things like that, and capacitance. Okay, now let's see. You were doing in your homework, it might have caught some of you off guard because I really stepped you through. The solution really helps you. I want you to provide the details, right? Once again, knowing the answer is only half of it. I want you to understand what you're doing. So even though I gave you the answers for the steps, you still have to provide the reasoning. And seeing the answer can often help you figure out what the reasoning might be. So you had a line charge, and you were to find the electrostatic potential at a distance y above the middle of that line. That the charge Q was spread out evenly over this line so that there's a linear charge density of charge per unit length. And then you were to make, and so the answer for that looks like, okay, let's see, I'm going to show you here in a minute. Well, I just write it down here. Phi, depending on y here, goes like lambda natural log, what was it? Is it L? L plus, yeah, L plus 4y squared minus L plus L squared here. L squared plus 4y squared. Okay, that's what that looks like. And then you were to demonstrate that for y much less than L, that this goes like 5y goes like negative 2 lambda natural log of y over L. Okay. Or 2 lambda natural log L over y. Okay, now the natural log here of y over L is equal to the natural log of y minus the natural log of L. And so we were using before this first piece minus 2 lambda natural log y. We determined that by applying Gauss's law for close to the wire. So if y is small, if you're in here, in this distance, we can approximate the electrostatic potential by this. And then there was this. Now we discovered that there's this additional term here, which is a constant, doesn't depend on y, and so we treated it as a constant. And that has to do with the reference there for the electrostatic potential. Okay, so I wanted to show you what that looks like here. So let's switch over here. Hang on. Okay, so I'm going to set L equal to 1 and show you a plot of what this looks like. So this piece right here is the electrostatic potential. Along that midline, again, setting L equal to 1, and then doing the Taylor series. This is the Taylor series approximation of that same thing here. And so this is the plot of the electrostatic potential. The blue line here is the exact result, which is the more complex result. And the yellow or goldish line is the Taylor series approximation that goes like log y up close. And so you can see it approaches the exact result. And then if as y gets here to be close to about a third or 1/2, now the approximation is getting less good. And so you can see up here the argument that you're close to the wire and far from the ends is a good approximation of the exact result. And you now know how to get the exact result. And you can see now that the approximation gets worse as you get farther from the line. Okay, now I want to show you what the full potential looks like around that wire. I don't want to do it just along the midpoint. I want to do it for any point. We've got this long wire, and I want to find the electrostatic potential anywhere. And so you can do it again by doing an integral. Here's the integral that you can do. It's very similar to one that you did, just the limits could be different. That's one way to do it. Here's the electrostatic potential as a function of x and y, where the origin is placed in the midpoint of the wire. The wire is along the x-axis here. That's what it looks like, and I'm going to plot that for you. Here's the plot. Let me see if I can. Okay, good. Expanded. All right. Those are the contour plots of the electrostatic potential. And I've excised from the plot here, right there, because that gets very singular. The electric field gets enormous. In fact, unbounded. It grows a lot right on the ends, and so it gets very difficult. The contours get really close together, and so I've told it not to plot that part. Okay, so now you can see what the contour lines look like. If you get far away, well, let's get up close here. As you get up close, well, that's what you did right there in the middle, right? It's that what I just showed you across here. It looks like logarithmic in y across here. And the electric field would go like 1 over the distance. Remember, the electric field is related to the gradient, and the gradient is given by the spacing between these contours, the slope. So the spacing gets farther apart, so the electric field is dying off as you get away from it. Okay. Notice that these contours pile up here right around the ends. The electric field gets really intense at that point on the ends, which is why a lightning rod is a line. right? It's a pointed piece of wire. The electric field gets very intense, and if you're trying to attract discharge, you can attract it by having an end like that, which will generate a high electric field and cause the discharge to happen at that point. And if you get farther from the line, look at what the contours are doing. They're getting almost circular, which means that as you get far away, the field is looking like a point charge of magnitude Q, and the potential, electrostatic potential, will go like 1 over R, Q over R. Right? And you can see it's getting more circular, and if we get farther away, it'll get closer and closer to circular, because the length of the line is getting, you're getting far away, and it looks like it's all concentrated at a point. The length of the line becomes irrelevant. Okay, so the point here is that this is the way, using this integral that we did for phi, and then there's a similar one you could do for E. You could get E from taking the gradient of this function. That would give you E, or you could get E by doing the integral like you did. Either way, now you know how to calculate the exact electrostatic potential and electric field around a line charge, and to do it around any sort of arrangement of charges is basically the same. Just now you're perhaps doing a two-dimensional integral if you have a two-dimensional distribution, or a volume integral if you have a full volume distribution. Okay, but in principle, you can calculate these things exactly. Calculus is a great way to do it. So it's a nice exercise in calculus to calculate these fields. Okay, any questions about that? Okay, so let's return to the lecture. Oh, let's check this. Where are we? Oh, we're in the dark. We messed up. It took too long. It's over Russia, but in the dark. That's too bad. Okay, now I'm going to close this. Okay. All right, going back to this now. Let's see here. Okay, any questions generally about the chapter? I'm going to start a review. So this would be a good time for something that you had lurking in the back of your mind. You haven't figured out how to ask it. Now's a good time to try to figure out how to ask it. What are you confused about? There's a lot of material in Chapter 2. I'm going to take a step back here for a second in the sense to give you an overview of what's coming. Chapter 2 has a lot of mathematical development, like what happened in the first volume. In mechanics, the second chapter consisted of the development of vectors and calculus, derivatives, a little bit of integrals we did, not much. We saved that for later. There was a lot of that in Chapter 2, and some of that may have been familiar to you and some of it less familiar, but it was a lot of math. For those for whom it was all new, seemed like a lot to swallow in one chapter, but we kept using it over and over again as cross product, dot product, and so forth as we went into later chapters. But the bulk of the new math was in that chapter. Okay, same thing is happening in this volume. Electricity and magnetism, there's a slug of new math. Now, most of this may be unfamiliar to you, right? There's going to be a greater fraction of the class will have never seen a divergence or a curl or surface integral, things like that. So more of you now are going to be thinking, wow, there's a lot to learn here, and there is a lot to learn. But even if you have seen, in both cases, in the mechanics and E&M, even if you've seen the math before, you probably didn't understand it as well as you could. And Dr. Rizzi is providing a really good presentation of it with this basic understanding that math is quantity. Math is the study of quantity, and it's the focus of mathematics. And so he really provides a deeper insight into the mathematics than I think that you get in most mathematics classes. But my point here is that the second chapter is, again, there's a little slug of math here. We're doing divergence and curl. Haven't done much curl yet. It's coming more. Anyway, we've got a lot of math here. It's going to be used throughout the rest of the course. So it may seem like there's a lot of stuff to learn here at the beginning, and there is, but it's going to keep coming back again. We'll see it over and over again, and so it'll give you a chance. But you really need to concentrate on making sure you understand the math really well at this point. And, of course, he's introducing the electric field and electrostatics at the same time. And so that's the other part that you need to get down. Okay, so any questions, or shall we just kind of start reviewing? Okay, so I think maybe a good time at this point would be to review some things from the practice test, but I'll pick some things that aren't on the practice test. Well, I don't know. Maybe we should go ahead and just start the basic principles. Let's start with that. How about a substance? What is a substance? Something that exists of itself. And a property. Something that exists of something else, which would be a substance then, right? Okay. Give me an example of a substance that we've encountered in this class, this semester. Pardon? Plana. Right. Give me an example of a property of the plana. Electric field is a property of the plana. Electrostatic potential is a property of the plana. We've also encountered massive substances. That's a holdover from last semester. That's an example of a type of substance. Property of a massive substance that we've introduced this term that we didn't have before. Charge. And now we're going to, in addition to that, have impetus, which we are familiar with from last term. So now we have charged massive bodies, some of which may have impetus, which gives it now a new twist, right? Combining the plana with charged substances in the plana, possibly with impetus. Okay, so that brings us back to impetus then. Impetus is still a key concept. So do you remember the definition of impetus?
Power activated in a body that moves it in a uniform linear direction to constant speed.
Okay, yeah, the direction is not uniform. In a fixed linear direction at a uniform speed. Good, yeah. And the power is what category of property?
A quality.
It's a quality of the body. Okay, and then charge is what category? It's a property. What category?
Quality.
It's a quality. Yeah, that's right. Quantity is very limited. Quantity is basically extension and having parts outside of each other. Quantity is a very limited category in that sense. And in terms of all the things you can think about, in terms of all the properties that bodies could have, quantity is very limited in that. It's very narrow in that sense. So a lot of the things that we think about, charge, mass, impetus, are qualities of the body that can be measured. These are measurables, which is an analogy to quantity. So these are measurables, and so hence you often hear them referred to as physical quantities, but that's a mistake to say. That's a confusion, right? Because they're not quantity. How about electric field? We said it's a property of the plana. What category? Quality. I think you said that. Okay. But you should know those a little bit better, right? There's the short definitions that I've provided on Blackboard, so you should be able to recant those, recite those, not recant them, recite them, regurgitate them on the test. Okay, so what is the cause of an electric field?
Charge.
Yeah, more precisely, a charged massive body in the plana, right? Acting on the parts of the plana around it. Okay, let's see, there was a diagram of substances. Oh, what's going on there? Different types of substances. Starting with broad division first. This was a tree. Yeah, before that, there was even a higher division before we got to massive. It was physical or material substances and non-physical or immaterial. Did he have that in there? I think that was in there. At the very top division or not? Okay, so among physical substances now, division was, yes, massive and non-massive. The only non-massive substance we have encountered so far is the plana. We've had lots of massive substances. We kind of group them together, but there are lots of things that we would call massive substances.
Are there other non-massive substances?
Not that I know of. Okay, so and massive substances can't have charge, so I guess you could have a further division about charged, but that's second nature to the body. It's not really a good way to make this categorization. Okay, I've forgotten the rest of the diagram.
Living, non-living?
Ah, there you go. Thank you. Yeah, living and non-living. And non-living was further broken up into elementary and complex, right? There was elementary and then complex non-living things. Living could be further divided into plants, animals, man, so forth. Okay. Okay. So again, this is from the most generic towards the most specific. So if you wanted to say what is the plana, you would work your way down this chart. Well, it's a substance. It's not a property. It's a substance which is physical, non-massive, a non-massive physical substance. Right? That's an understanding of plana. Whereas a piece of copper would be a complex, non-living, massive physical substance. So you can understand things that way, working from generic to specific. Okay, so going to the case of plana, you should be able, the electric field, you should be able to explain how it is that an electric field is results from the charged massive body acting on the parts of the plana around it, and then this propagates outward. Okay. So we could distribute the charge if we started off with a charge that was confined to something like a point, really small volume. How does the electric field depend on the charge and the distance?
1 over r squared.
Yeah, electric field goes like Q over R squared. And the electrostatic potential is what? What is the electrostatic potential?
Q over r.
Yeah, empiriometrically it's Q over R. Let me ask more generically, essentially, what is the electrostatic potential? So the substance is a property. It's a property of the plana. Category quality. It's a further specification of the electric field. Okay. So, and then if we put a test body over here, we would get a force and a potential energy as a result in the system. And the force would be a nice way to write it is this, where the force and the potential energy are proportional to the electric field and electrostatic potential. Okay, I have a question for you. Here's a little side question. Suppose I have an electric dipole here. I have a little bar here, and it has on one end it has a positive charge, and on the other end it has a negative charge. Okay, so what's going to happen to that dipole if you pin the, well, first, is there a net force on the dipole? Not like this, no, because it's the same distance. Is there a torque on the dipole? Now, which way does it want to turn the dipole? Yeah, it's going to repel this one and attract this one, which emphasizes that the electric field has the opposite effect on different kinds of charge, right? The positive charge will move in the direction of the electric field, and the negative charge will move in the opposite direction. So it torques the dipole. It wants to twist it so as to align the dipole this way. Now there's actually a small net force on the dipole. Why?
The distance.
Yeah, the distances are different. The negative charge is closer, so will it be attractive or repulsive on net?
Attractive.
It's going to be net attractive, a little weaker than it would be if you just had a bare. It's going to be weaker than if you had a bare negative charge because it has an accompanying positive charge. But there's going to be a weaker attraction to the dipole in this case. Okay, now that's because the electric field is not uniform, right? The electric field is stronger in one place than it is in another place. So there's a net attraction to the dipole when it's aligned like that. So which of these two configurations of the dipole has higher potential energy? The first has higher potential energy, right? Bodies want to move towards lower potential energy, right? Okay. Okay. Okay, under what conditions does the electrostatic approximation? Well, first, what is the electrostatic condition? Let's just say that.
Bodies are non-moving.
Yeah, the charged bodies don't move. Everybody's stationary. Okay, so now, and keep in mind here, I could have a bunch of charges like this, and I want you to calculate, say, the electric field at this point or phi at that point. This would be done by a superposition of either vectors or numbers, right? If I bring in I want to know the electric field at some point, and that would give me the force on the test body if I brought the test body in. But notice that when I talk about bringing in a test body here, I'm keeping all the other charges fixed. I don't let them rearrange, right? So you have to keep that in mind, because if I had a piece of metal which had a bunch of charges on it that's generating an electric field, but the charges are arrayed on the metal like this, if I'm going to bring in another charge here, if those are on a conductor, they'll move, they'll rearrange, because I've brought in another charge. So you have to keep that in mind here. Conductors have the ability to rearrange their parts, the charged parts, so they move around in response to new electric fields. So you have to keep that in mind, and usually what I mean here is in the electrostatic approximation, they're fixed and not allowed to move around. And so I can calculate the electric field, and then if I brought in a test charge, they're fixed, they can't rearrange themselves, so now I would be able to calculate the force on that. If they were allowed to rearrange themselves, the electric field would be different now. And the force on this body, I'd have to take into account the rearrangement. It gets more complicated, right? So the electrostatic approximation is, let's simplify it, don't let things move around. That's the electrostatic condition. What's the electrostatic approximation? Exactly, infinite speed of propagation. So if I have a charge here, Q, the electric field over at this point is Q over R squared. Okay, now let's move this charge over here. What does the electric field do? It moves instantaneously to reflect the new position of that charge without delay. So you're saying that this motion of this charge is slow enough and this distance involved is small enough that I don't worry about the propagation time that there would be. If this distance were light years, then it would take years for this to alter the electric field out there, right? If I have a charge here, there's an electric field generated by that light years away. If I move this charge now, it's going to take years for that to propagate outward out there. So clearly there's situations where we have to take into account that propagation. We're not going to get to that until chapter 6. Okay, so that's the electrostatic approximation, is you don't worry about the transmission time. How long does it take? Okay, so what is the dimensionality of rho if that's a volume charge density? Notice that I used this symbol rho earlier in the talk today to be resistivity of a material, right? Be careful here. The symbols get reused and recycled and stuff. So, yeah, I have to tell you exactly what the symbol is supposed to represent. Volume charge density. So what would the dimensionality be?
Q charge.
Right. Surface charge density. Right, Q over L squared, Q over area, and linear charge density is just Q over L. And usually what happens in this case is, at least in the problems we're dealing with, these are uniform charge densities. That is, there's some uniform lambda. But in principle, lambda could depend on where you are. You could have more charge clumped up on one end of the line than somewhere else. So these could be not uniform, but we usually consider them for the sake of simplicity when we're learning this, that this is a uniform distribution. Okay, how about the volume current density? The dimensionality of volume current density.
Charge per area?
Charge per area, well, there's a time involved. There's a rate, right? A current has a rate in it. And how about just the current, what's called the current?
Charge per time.
Charge per time. The relationship between J and I then is J times an area gives you a current, total current. So it's the total charge per time flowing past an area. Now these are electric. What we're talking about here is current, but he also was talking about density. Excuse me. Man, this is loud. I wish I could turn that down a little bit. Okay. So we have now, we're talking about here current in terms of charge, right? But we also talked in the development of this mass. So we would have a mass analog for this, a mass volume current density and a mass current. So instead of charge, we'd have mass. And he also talked about just volume, just moving a volume of fluid. And so we would have then a volume. Okay. Now also, what is the relationship between the volume current density and the volume charge density?
J equals rho times the velocity. Right?
Times the velocity. How fast are the charges moving? So if I have a certain density of charges and they're all moving in a certain direction with a given speed, now I have a volume charge density, which is just expressed as the product of those. Okay. We'll come back to the current in the next chapter when we consider magnetic fields. We're going to look at the magnetic fields around current carrying wires. So the current doesn't play much role in electrostatics because things aren't supposed to be moving, right? So we'll come back to that. Okay, how about what is Gauss's law? I want both the differential and integral forms.
The double integral over the surface integral over the surface of the electric field dotted with the dA equals 4 pi q.
Right, inside the volume. And this surface bounds the volume. How about the differential form of that? Divergence, yeah. Divergence of E is
4 pi rho.
4 pi rho. Good. Rho is the volume charge density. So tell me about dA. What is dA? So,
It's a small square of the area with
Okay.
a normal vector to the area,
uh-huh. And what is the direction of dA?
normal to the area.
Yeah, it's normal to the area. And in this particular use here, in Gauss's law, there's a particular direction for dA, right? There's two normals to an area, upper one direction or the other. We choose one.
Outward.
Pointing outward. Yeah. So that only works if you have a complete surface that bounds a volume. If you have an incomplete surface, there's no in or out, so you have to tell me which direction is which. dA is not specified, but in Gauss's law, the convention is to choose it to point, surrounding a volume, you point outward from that volume. Okay, very good. Okay, and so these are known also as Maxwell's first equation. In fact, really the first equation usually is expressed in differential form. You don't usually see it as expressed in the integral form, but it is the same content, and they're related by Gauss's theorem. What is Gauss's theorem? Go ahead, Mr. Bico.
I have no clue. Is it like del E?
It's related to the divergence, yeah.
Is equals
I'll give you a hint. There's a surface integral on one side and a volume integral on the other side. Ah! You had to look it up. All right, this one you need to work on. So Gauss's theorem is the volume integral of the divergence is the same as the surface integral bounding that volume of the flux. J can be anything, any vector field, any reasonable vector field that's differentiable and so forth. Okay, need to remember that one, learn that one. And so I need to let you go. Finally, so the next thing I was going to ask is the fundamental definition of the divergence of some field, and also the Cartesian form of the divergence of some vector field. And you should be able, of course, to calculate, if I give you a vector field, to be able to calculate in Cartesian form, be able to calculate the divergence of that, carry it out. So I guess we'll get to that on Monday. All right. Have a good weekend. See you then.
Professor.
Yes,
Can
sir.
I make a quick announcement?
Go ahead.
SPS